and welcome to this video. This is on the Edexcel IAL Chemistry Unit 1 paper, the core principles of chemistry. This video is obviously for the internationals. My name is Chris Harris. I am from alawistutors.com. I also run a chemistry-based bit of that, which is called Alawi Chemistry. It has podcasts and a YouTube channel, which you may have found this on, and we do resources as well, revision resources and teaching resources, etc. via the TES and via alawistutors.com. So, yes, so this video, basically, we're just going to go through this past paper. The idea is that we're going to go through the answers, and I'm going to explain what the answers are, because quite often, obviously, you can look through a past paper and look through the mark scheme, but it doesn't tell you why it's the answer. So I'm going to go through them. Obviously, it's just as important as knowing the content as being able to answer the exam question, and also give you a few little hints and tips along the way as well to try and help you get the best answers you possibly can by using keywords and understanding the question. So yeah, so let's crack on with this one. So start with question 1. I should also point out, make sure you read the questions really carefully. That's really important. With these ones, obviously, just put a cross at the box. But if you change your mind, put a line through it. The number of times people will get this wrong, and they won't get credit for it because they haven't followed the instructions. It's so simple. So, right, let's start with the first one. So it says, in which order do the electrons fill the orbitals of an atom? So we've got a series of different electron orbitals, or the electron configuration, should I say. So we've got the first one, 1s2, 2s2, 1s, 2s, 2p, 3s, 3p, 4s, 4p, and 3d. Now these ones are the wrong way around, so it's not that one because they're back to front. 1s, 2s, 2p, 3s, 3d, 3p, 4s, 4p. So yeah, we've got a problem here. This 3D isn't in the right place, so that's wrong. That should be a little bit further up. In fact, it's definitely out because it comes between 3s and 3p, so that's not right. C, 1s, 2s, 2p, 3s, 3p, 3d, 4s. Right, these two are the wrong way around. So it only leaves us with D, and this one's correct. So it's always your 4s is lower in energy than your 3d. So this one is going to be D. Okay. Right, question 2. Ions are separated in the mass spectrometer by. So you need to know this. You've got different parts of the mass spectrometer. The vacuum pump, all that does is just pulls the ions through. It creates a vacuum and encourages them to move through the kind of chamber without touching any other molecule. Because obviously, if it was full of air particles, then these particles could collide with the air. So it's definitely not A. The magnetic field, yes, that's the thing that actually deflects them. This deflects the ions as they pass through, and depending on the mass of the ion will depend on how much they're deflected. So effectively they are separated. So yes, that is it. Let's have a look at the other ones anyway. Ionization chamber, no, that's just the area where the atoms are ionized. They're not separated at that point. Electron bombardment, that's obviously what ionizes them. So this one is actually B, magnetic field. Okay. Part 3. Which of the following contains 1 mole of neutrons? Okay, so what we're going to do is work out some moles here. We're going to look at the number of neutrons as well, because obviously that's quite important. The first thing I think we can definitely discount is this one. It doesn't have any neutrons, so it's definitely not A. If we look at B, all we're doing is working out the number of moles. Now, the number of moles, remember, is mass over mR. So we just make a note of that. We'll write that in blue. So moles equals, and that's mass over mR. Or in this case, it's going to be AR, isn't it? Because it's the atomic mass, so it's mass over AR. So yeah, so let's work out this one. So this is going to be 1 over the atomic mass is 12. Now I've already worked these ones out because it just makes it a little bit quicker. So it's 0.083. That's the number of moles, but the number of neutrons in here is 12 minus 6. So remember, we're looking for the number of moles of neutrons. So we're going to times that number by 6 because we've got 6 neutrons in here, and that gets me 0.5. If we do the same for this one, 2 divided by 24, because that's the mass, and that would give me 0.083 again. Okay, number of neutrons here is 24 minus 12, so that's going to be times by 12, and that's going to give me 1. So far so good. That one gives you 1. That's obviously going to be the answer. But let's have a look at this one anyway. The next one, 2 out of 22. That equals 0.083 as well. No, it doesn't. It equals 0.09. Apologies. Number of neutrons is 22 minus 10, which is 12 neutrons. And that's going to equal 1.08. So not quite 1 mole. So the answer is C, because that one gives you 1 mole. Remember, it's 1 mole of neutrons. That's what we're looking for. Okay, right. So the next bit, which is question 4, says the solutions of barium chloride and silver nitrate are mixed together. The reaction takes place, or the reaction that takes place is an example of. Right. Now, what we're going to form here is, well, obviously we're going to get barium nitrate and silver chloride. Now, barium nitrate, you won't see anything because it's soluble, but silver chloride is insoluble. You actually get a precipitate. Silver chloride is white. You might have heard of it from the other ones as well, like silver bromide, which is cream, and silver iodide, which is yellow, which is a test for halide ions. So because we're getting a solid forming in solution, we call it a precipitation reaction. So this one is D. Okay, so that's basically just you trying to identify one of the compounds and knowing that you form a solid. Okay, question 5. The Avogadro constant is numerically equal to the number of. Right, Avogadro is basically the number of atoms or molecules in 1 mole of a substance. So that's really important. So we're just looking for an answer that matches that, really. 8 ions in 1 mole of sodium chloride. No, that wouldn't be the case because you get 2 ions here per molecule, so that wouldn't answer that one. B, atoms in 1 mole of hydrogen gas. No, that's atoms in 1 mole of hydrogen gas. You get 2 atoms here per molecule, so that doesn't meet Avogadro's constant. Electrons in 1 mole, no, it's got nothing to do with electrons, so we can miss that one. So the only one left is D, and this is because it's molecules in 1 mole of oxygen gas. So we're looking at both of these. How many of these do we have in 1 mole of a substance? So that's what Avogadro's number is telling us. So that one is correct. That one is D. Okay, question 6. 10 grams of magnesium is added to 1 decimeters cubed of 1 moles per dm cubed copper sulfate solution, and the mixture is stirred until no further reaction occurs. Which of the following is a result of this reaction? Right, what we've got to do is we've got to work out the number of moles of both of them, because we're going to try and work out how much we might have more of one than the other, and it looks likely because it's starting to talk about these answers here about all the magnesium reacts, etc. So if I work out how many moles of copper sulfate I've got and how many moles of magnesium I've got, it might give me an idea of what might happen with my reaction. So let's work out the copper sulfate first. So copper sulfate is, let's just do this in a different color. Let's pick green, light green. So copper sulfate is the, basically to work out the number of moles. So remember, moles is concentration times by the volume. So the number of moles in this case is going to be 1 times by 1, because we've got 1 dm cubed and 1 moles per dm cubed, which is going to give us 1. That's dead easy. And the number of moles of magnesium. Okay, so remember moles in this, because this is a solid, this is going to be mass over AR, which is the relative atomic mass of magnesium. So in this case, the mass is going to be 10. The relative atomic mass of magnesium is actually 24. And so we do 10 divided by 24, it's going to give us 0.416. Okay, now what you can see here, so that's moles, not grams. So that's moles. Okay, so what you can see is we've actually got less moles of magnesium than we do copper sulfate. Now what that means is that all of our magnesium will react, but we will have some copper sulfate that's left over. Now this is important because actually, if we look at the first one, it says the resultant solution is colorless. Well, copper sulfate's blue, it's a blue solution. If all of it, some of it is left over, even after the full reaction of magnesium, if we use up all these moles, we'll still have some of this left. The solution is going to be still blue, so that's not true. 10 grams of copper is displaced. No, just because we've used 10 grams of magnesium, it doesn't mean we're going to produce 10 grams of copper. Remember, a copper atom is bigger than a magnesium atom, so mole for mole, it's going to weigh more anyway. So that isn't true. 63.5 grams of copper is displaced. No, that's assuming that this is obviously assuming that we've used up all of the copper sulfate. We can see here that we can't do that because we don't have enough magnesium to do that. We haven't got the same number of moles, so that can't be right. So the last one has got to be right. All the magnesium reacts, and that would be true because you've got 0.416 moles of magnesium, but you've got 1 mole of copper sulfate. It says the reaction doesn't go any further, so that assumes that obviously we've ran out of magnesium. It's all reacted, so that's the answer, which is D. Okay. Question 7. Right, so question 7. It says, which of the following gas samples has the same volume as 7 grams of carbon monoxide? All volumes are measured at the same temperature and pressure. Right, okay. So what we're going to do is we're going to have to work out the volume of carbon monoxide that we've actually made. Okay, so we're going to use, let's just write this in green. So the number of moles, so we'll have to work out the number of moles first. The number of moles is mass over the MR of carbon monoxide, which is 28, if you work that out using your periodic table. And that should get you 0.25 moles. Okay, and then what we have to do is we have to work out the volume. Now, to work out the volume of a gas, we take the number of moles, and we multiply it by 24, which is going to give us our volume in decimeters cubed. And the 24 bit is actually the volume that 1 mole of a gas will occupy at room temperature and pressure. So you need to remember that number. So you'll see it quite a bit. So this time, obviously, it's number of moles, 0.25, times by 24. And that's going to get us 6 decimeters cubed. Okay, so we're looking for a number that matches that effectively. So we're going to do exactly the same calculation. We're going to do these ones in red. We're going to do it for each one of these. So we're going to do, obviously, 1 divided by, this one's hydrogen, H2 is 2. Okay, remember that's H2. It's diatomic molecule, so it's 1 divided by 2. You don't need to be a mathematician to work that out. That's a half. We're going to times that by 24. Because that's the volume in gases for 1 mole of a gas at room temperature and pressure, and this is going to give us 12. Okay, so that's 12 Diem cubed. You can see that one doesn't match, so we're looking for 6. Okay, this one 3.5 divided by the atomic mass of nitrogen. Remember, it's N2, so that's going to be 14 times 2, which is going to be 28. So 3.5 times 28 is 0.125. Okay, multiply that by 24. That's the volume of the gas. And that's going to give us 3 decimeters cubed. Again, it doesn't match the number that we've got here, so we keep going. This one is going to be 10 divided by the argon. Atomic mass of argon is 40. You should get 0.25. Times that by 24. And that should give us 6 decimeters cubed, which does. Spot on. That's our answer there. Okay. And just to prove it, let's just quickly do this one. So this one's going to be chlorine, which is 35.5. We're going to divide that by, because it's Cl2, so it's going to be 35.5 times by 2, which is going to be 71. And that's going to give us 0.5. We're going to times that by 24. And we should get 12 decimeters cubed. So you'd see that obviously that one doesn't match. So the answer is C, because that matches. Okay. Question 8. Which of the following aqueous solutions contains the greatest number of negative ions? Right. What we have to do is just work out the moles of all of for the full molecule. And then once we know that, we can then multiply by however many negative ions we've got in that molecule. So let's work this out. Let's go for green this time, shall we? Right. So to work out the number of moles, because that's going to tell us about the amount of negative ions in there. We do concentration times volume. Remember, the volume's got to be in decimeters cubed. So we're going to put moles equals concentration is 0.1 times by the volume. Now, to make it easier, I'm just going to put that times by 10 to the minus 3 means exactly the same thing as divide by 1,000, which is going to get you into decimeters cubed. So this one should give us the number of moles of 0.05. Now, you can see that this is the number of moles of the full molecule, but we only have one negative ion in there, which is the sulfate. Sulfate is SO4 2-. So the number of moles, that equals the number of moles of sulfate as well. Okay, let's look at the next one. So mole. Again, we're going to do the same thing. Concentration, 0.12 times by the volume, 250 times by 10 to the minus 3. And that's going to give us a concentration of a mole, of 0.03. But look, we have two of them. They're Cl minuses. This is the number of moles for one molecule, but because each molecule produces two lots of Cl minus, because we've got Cl2, we have to double that. So we're going to times that by 2. So that's going to be 0.06 moles of Cl minus ions. Okay, the next one, the number of moles is 0.15 times by 250 times by 10 to the minus 3. Okay, so we should get the number of moles to be 0.0375. Okay, now because we only produce, there's the I bit, that's I minus, because we only produce one of them, then that is just the number of moles of I minus as well, because there's one I minus per molecule, so that's just that. And the last bit is mole equals the concentration, which is 0.1 times by 500 times by 10 to the minus 3. And that's going to give us the number of moles is 0.05. Now, this bit, this is a nitrate ion, which is there. Nitrate is NO3 2-, but we've got two of them. So we'll have to multiply that by 2 to get the number of moles of the negative ion. And that's going to give us 0.10 moles. Now, if you look at the answers here, we've got 0.05, 0.06, 0.0375, and 0.1. This one is obviously the biggest one, so the answer to this one is D. Okay, a lot of work with that one, as you can see. Number 9. In an experiment carried out at 200 degrees Celsius and 1 atmosphere of pressure, 20 centimeters cubed of ammonia gas reacted with an excess of heated copper 2 oxide. And we've got the equation there. If all the measurements were made at 200 degrees Celsius and 1 atmosphere of pressure, what would be the total volume in centimeters cubed of gaseous products? Right, now, what we're going to do is we're going to kind of section this bit off. So we've got 20 centimeters cubed there. Okay, but if you look at the total number of gas products we're producing there, that's the only gases. We've got 4 there. So if we're producing 20 centimeters cubed and this was worth 2 ammonia, 4 is going to be double that. So 2 to 4 is double. So 20 double 20 is 40. It's as simple as that. So it's 40 centimeters cubed. And so the answer is D, 40. So just look at your mole ratios. But the key thing there was total volume. So that is basically both gases. That's what they want you to look out for. Okay, so right, on to the next one, which is question 10. Right, question 10. Ammonia is manufactured from hydrogen and nitrogen in the Haber process. You can see we've got the reaction there. 60 tons of hydrogen produces 80 tons of ammonia. What is the percentage yield of the reaction? Okay, the first thing we need to look at is the percentage yield. So the yield is the actual amount divided by the theoretical amount. So the actual amount we have produced of ammonia is 80 tons. So basically, you see these options here, C and D don't have 80 on the top. So we can immediately discount C and D because it's not them. So we're looking at these two because they've both got 80. That's the theoretical mass. The actual mass, sorry. So now we need to work out what could we produce in theory. So it's a really simple way of doing this, actually. We're going to start with 3H2 and 2NH3. So what we're looking for is basically we're going to take the relative atomic mass of hydrogen and multiply it by 3. So hydrogen's 1, 2 of them makes it 2. So H2 is a mass of 2. Times that by 3 is going to be 6. So we're going to put 6 there. This one is going to be 14 plus your 3 hydrogens, which is going to be 17. 17 times by the 2 is going to get you 34. Okay, and all we do is we want to basically, remember we had 60 tons of hydrogen. We want to work out in theory how much ammonia could be produced with 60 tons. So a way to do that is to basically, you divide to find 1 and you multiply to find 60. So 6 6 divided by 6 gets us 1. And we've got to do exactly the same on the other side. So 34 divided by 6 is going to give us 5.6. Okay. And then obviously to get from 1 to 60, we times that by 60. And we do exactly the same on that side, times that by 60. So 5.6 times by 60 is going to get us 340. So in theory, 60 tons of hydrogen should produce 340 tons of ammonia. So this is the number here. In theory, we should get 340. So the answer to this one is going to be B, which is 10. Okay. Question 11. Which of the following compounds is the greatest ionic character? Right, so we're looking for your periodic table, basically, and you pick the metal that's on the bottom left-hand side, so in group 1, and you pick the non-metal furthest up and right, excluding group 8 and group 0, so that would be fluorine, and you're basically putting these two elements together is going to give you the most ionic character, the greatest ionic character. So you're basically wanting very little distortion in the electron cloud, and you want nice point charges, nice and neat. So if you look at the periodic table, you'll find that cesium is somewhere down towards the bottom left. So it's not very polar whatsoever, a big atom. And fluorine is really electronegative. So these are going to be really pulling electrons quite well. So because we've got two opposite ions, this is going to give us the most ionic character. Iodine's a little bit further down than fluorine, so it doesn't pull the electrons that much, so you get a bit of distortion there. Potassium isn't as low down as cesium, it's a little bit higher up, so again you get a little bit more distortion with potassium, and then obviously these two are least ionic character. So the answer here is cesium fluoride. Okay. Number 12. Which species has a dative covalent bond? Right, so let's draw out, let's see what we've got. So oxygen is O double bond O. OH is that, you got negative charge on the oxygen, no dative covalent there. Water is OH2, no dative covalent there. This one is though. So what you have, if I draw it like 3D, you have a lone pair on there. There is your dative covalent bond. H3O plus is classic dative covalent bond or coordinate bond. Basically, both electrons from the oxygen have been donated to the hydrogen because it didn't have any. So that's a dative covalent bond. Ammonium is another one, which is NH4. That's another one which you might want to look out for as well. But anyway, the answer to that one is H3O plus. Right, question 13. So we've got the atomic radius of potassium is larger than that of sodium because potassium has. So we've got to look for the radius of potassium. It is lower down in group 1 than sodium. So that means it's got an extra electron shell. That makes it significantly larger than the sodium atom, which is a lot smaller. So that's the key thing, really. When you go down a group, the biggest change in atomic radius is the more electron shells, and they're occupied as well, obviously. Larger nucleus doesn't have that effect. Yes, it does have a larger nucleus, that's true, but it's not having an effect on the overall size of the atom. Larger nuclear charge, that has nothing to do with it, and it does to an extent if you're going across a period, because a larger nuclear charge would actually pull the overall radius slightly further in as we go across the period, but it's got nothing to do with this because we're going down a group. And D, a smaller first ionization energy, has got absolutely nothing to do with this, so we don't need to worry about that. Okay, question 14. Consider the following data. Okay, so we've got a few reactions here, and we've got some enthalpies. What is the relationship between A, B, C, and D? Okay, so all we have to do is basically say, look, we've got A here, and is the equation A, does this fit with B plus C minus D? So does that fit? So all we're going to do is just going to try them, and literally just where it says B, we're going to write the equation. It's a bit like algebra. So equation B, let's write this down. We're going to do this in, let's do some blue, shall we? Right, so we've got H2 plus half O2, and that will give H2O. Okay, so there's your first one. And we're going to add that. Let's get C in there as well. So S plus O2. And that will produce SO2. Okay, so we're going to add all these up. So that's going to give us H2 plus S plus we've got 1.5 O2, and that's going to produce H2O plus SO2. Okay, so we've added them. Now, when it says minus D, all we have to do is basically just flip this equation around. It's just doing the opposite, so we're doing negative. So instead of putting H2S plus 1.5 O2, etc., etc., we're going to put it the other way around. And what we're going to do, just so we don't get ourselves confused, I'm going to do it in green. Okay, so I'm going to put H2O there, plus SO2, and that's going to form H2S plus 1.5 O2. Okay, so we're going to add these two together. Now, this is where the magic bit happens. And what we're going to do is we're going to cancel a few things off because we've got quite a few things here. So you see we've got SO2 here, there, and that cancels out there because we've got one on the left and one on the right, so we cancel that out. 1.5 O2 there, 1.5 O2 there, so we cancel them out. So that's great. Waters, cancel them out, because that's on the left and that's on the right. As long as they're on opposite sides of the equation, that's fine. Then we look at what we've got left, and you can see what we've got left is just our final equation. H2 plus S, there they are, and that will produce H2S. There it is. Okay, check, does that match A? The answer is yes, it does. S plus H2 forms H2S, so actually the answer is A. Thankfully, otherwise you might have to have checked the rest of them. So, but yeah, because we've got the right answer, then that's fine. Okay. Right, question 15. Okay, so question 15, it says, in which of the following does X represent the mean bond enthalpy for OH bond in water? Okay, so mean bond enthalpy, so obviously we're looking at trying to break bonds, but let's just look at the molecule first. So we've got water. What we're going to do is we're going to break them two bonds there. And what we're going to form is an oxygen. And we're going to form two hydrogens as well. So we're looking for an equation that shows the formation of one O and two hydrogens. So these two, equation A and equation C, we can't have because they're forming molecules. We have to be forming two hydrogens. So it's either between B and D. Okay? So now what we're going to look for is say, right, well, B is, the enthalpy is for 2x, two lots of x, and D is for just 1x. But basically the mean bond enthalpy is the energy, the average energy or the mean energy for both bonds. We're breaking both of them. So because we're breaking two of them, it has to be 2x. And so this means that the answer is B. So I'm going to put that there. Okay, question 16. Which of the following is a step in the propagation stage of the chlorination of methane? Okay, right, so we're looking at these different steps. Now, we're looking for propagation. The first step is initiation, because we're turning a non-radical into two radicals. We use UV light to do that. So that's definitely not A. B, two radicals colliding together. As you can see there, you've got two radicals. That's forming a non-radical. That's a classic termination step, so that's not propagation, so it can't be that one. Let's look at C. We've got a radical and non-radical. Good. Okay, that's propagation. And we're forming a haloalkane and a chloride radical. Now, with this step, chlorination of methane does involve a methyl radical and a chlorine colliding together in one of the propagation steps. So actually, C is correct. If we look at D, D doesn't show that. Although D is showing a propagation process, because you've got a non-radical and a radical colliding together, it isn't showing us the process that we would have when we're forming the chlorination of methane. This process doesn't exist in that mechanism that you might have seen. So the answer's got to be C. Okay, question 17. A molecule Z has the following structure. We've got this molecule here. What are the total numbers of sigma and pi bonds in the molecule of Z? Right, remember, a sigma bond is just a covalent bond, a single covalent bond. Double bonds also have pi bonds as well. So double bonds have sigma and pi. Single bonds just have sigma. So all we're doing is we're going to score off how many bonds we've got here. We're going to use the red pen here. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 sigmas. Okay, and let's do it in a different color. The number of pi bonds, 1, 2, 3. So we've got 3 pi bonds there. So basically we're looking for 11 sigmas and 3 pi's. And the answer is C. There you go. Okay, question 18. So question 18 looks as though we're going to look at alkenes and EZ isomerism. So which is the structure of Z12-dibromoprop-1-ene? Right, so Z means the same side. So we're looking for different molecules. When we're talking about same side, we're talking about top and bottom, not left and right. So this is going to be Z. You can see here, this one is E, because you've got the same atom that is opposite the double bond. So that's an E one, so that's not Z. Same here, look, there's the same atom that's opposite the double bond, so it can't be B. If we look at C, we can see that we have got 2 bromines on the same side, and it fits 1,2-dibromoprop-1-ene. So 1, 2, carbon 1, carbon 2. This one isn't, because we've got a bromine attached to carbon 1, but this bromine is attached to carbon 3. So that'll be 1, 3. And so that isn't the case. So the answer is C for this one, because there you go, that's Z. So that's C. Okie doke. Right, on to question 19. So question 19, the skeletal formula for 3-methyl-cyclobute-1-ene, it's a bit of a mouthful, is shown below. You can see it there. So what is the skeletal formula of 1-ethyl 3-methyl-cyclopent-1-ene? Okay, so let's have a look at A first. Here it is. There's your pent, cyclopent, which is fine. We have an ethyl group hanging off the first carbon. Now remember, carbon 1 is where the alkene is. There's the alkene, there's carbon 1, and there is the ethyl bit there hanging off. So that is 1 ethyl, so that's fine. 3 methyl, so it's carbon 1, carbon 2, carbon 3, and there's the methyl group. So that's fine. And that's hanging off the third carbon. Remember, you count from here. Carbon 1, carbon 2. So that's fine. So this is your answer here. The rest of them don't obviously show that type of formation here. So that is the right answer. So that is A. So you've got to look out for the ethyl group hanging off the first carbon. Remember, it's cyclopent-1-ene. There's carbon 1. The ethyl group is hanging off the first carbon. So that's got to be A. Okay, so make sure you're looking for that. That's really, really important. Okay, and then on to the final one, which is question 20. Okay, which of the following fuels, when burnt, would make no significant contribution to climate change? Okay, when we burn a fuel, we produce carbon dioxide, which is a really potent greenhouse gas. So fuels, like particular fossil fuels, should I say. So fossil fuels are things like methane, petrol, and coal. They're all fossil fuels. So when we burn them, they produce carbon dioxide. However, the top one, when we burn hydrogen, all we produce is water. And water, yes, can go in the atmosphere and is a greenhouse gas, but it can fall as rainfall, so it can drop out of the atmosphere. And also we can collect the water as well and condense it. So that's pretty useful. So the answer to this one with no significant contribution to climate change is A, hydrogen. So that's it. So that's the end of section A. And now we're going to look at question 21. Okay, so this is question 21. Section B. So, a propellant for a rocket consists of a fuel, kerosene, and an oxidizer, liquid oxygen. So, rocket stuff. So, A, the formula of some hydrocarbons present in kerosene are shown in the table below. Right, so we've got loads of different molecules here. Okay, so it says the first thing is to name the homologous series to which compounds A, B, C, and E belong to. And you can see here they're all just carbons and hydrogens. We don't have any oxygens or anything like that in there, so this is just a bog-standard alkane. That's the homologous series they all belong to. So these are all alkanes. Okay, so that's your first one done. And then it says name compound A. Right, so we're going to go back to compound A. And compound A has a big long hydrocarbon chain here. So we're looking for the longest hydrocarbon chain. Either start from here or here, but it doesn't really matter. So we've got 1, 2, 3, 4, 5, 6, 7, 8. So we know it's going to be an octane. We've got a methyl group coming off here off the second carbon. And we've got a methyl group coming off the third carbon. So this should be 2, 3 dimethyl octane. So So let's put that there. We've got to make sure we obviously use the right terminology. So it's 2, 3 dash dimethyl. Don't forget the di bit. Okay, so dimethyl octane. Okay, so that gets you 1 mark. Okay, part 3. Explain the term structural isomers by a reference to 2 molecules selected from the table in part A. Right. Well, basically, a structural isomer is something that has the same molecular formula but different structural formula. So we're looking for something with the same number of carbons and hydrogens, but they're structured differently. Now, I can tell you that A and C do have the same number of carbons and hydrogens as each other. But the main difference is, look, this one's got a branch here coming off down here. This one doesn't. This bit is effectively just bolted onto the end here. So A and C are structural isomers of each other. So you can count the carbons and hydrogens there. So we're going to put A and C have the same molecular formula, but different structural formula. Okay. So, or you can say arrangement of atoms. Okay, so basically you're getting 3 marks. You're saying 1 for obviously identifying that A and C are structural isomers. They have the same molecular formula, gets you the 2nd mark, but different structural formulas is the 3rd mark. So that gets you all them 3 marks there. And then part IV, it says give the molecular formula of compound D. Right, so if I go back up to compound D, basically we're looking for, I just want to count the number of carbons and hydrogens we've got. Each one of these points here is a carbon. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 carbons. And the number of hydrogens, now what you've got is you've actually got 2 hydrogens coming off each one of these here. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We have 3 hydrogens coming off there, so that's 23. We also have 1 coming off there as well, so don't forget that one, which makes it 24. So that's C12H24. So yeah, you've got to really kind of, especially with skeletal, because it can be quite tricky to kind of spot. So if it helps, just draw it out. Draw it out as a displayed. So you get 2 marks for that. 1 for saying C12 and the other one for saying H24. So yeah, you know, a decent number of marks for these if you know what you're doing. So right, next question, part B. In the petrochemical industry, other fuels were obtained by cracking and reforming of kerosene. Now, you've got another difference. Cracking is taking a long molecule and breaking it down into shorter, more valuable or higher demand molecules. Reforming is where we take the molecule that we might have cracked and we change it structurally. We put branches on or turn it into a cyclic compound or something. So, using appropriate letters A to D, identify a molecule listed in the table that could be formed from E by cracking alone. Right, okay, so we'll have a look at E. There's E there. Okay, big long hydrocarbon. So we're looking for one that's shorter, but crucially not reformed. So not like that. So we're looking for something that has been cut. So this could be like this one. You can see here. Look, it's very, very similar, but this chain's shorter than that one, so that one's clearly been cracked. This one is shorter as well. If you count the number of carbons and hydrogens in here, it'll be less than this one here, and that's just basically a straight chain alkane. But what we can't do is add branching on like this. This one's got an additional branch added on. We can't do that through cracking. That's through reforming. So the only one really for E is A and B. So A or B, either one of them shows cracking. So we're going to put A or B. Okay. Part 2, cracking and then reforming. Right, so this is where we're adding the branching or the cyclic compound. So if we look here, take E. This has obviously been cracked because it is shorter, so is that one. But it's been reformed. So we've had a branch added on here, and we've added this one's got a cyclic compound here as well. So that's definitely been reformed. That was a bit more obvious. So that's C or D. Okay, right. So part C. Suggest how engine performance is improved by using a fuel containing the molecule of identified in B part 2. Right. Cyclic compounds and branching, what they do is they reduce engine knock-in. Basically what this means is, in a nutshell, your fuel burns much more efficiently, so you get less incomplete combustion, so it improves your miles per gallon. So we're going to put that down there. So reduces engine knocking. If I can spell. Okay, or you can say you've got more efficient burning. More efficient burning of the fuel. So anything like that, that would get you the mark. So that's what all branching hydrocarbons and putting things like cyclic compounds in there, that would do it as well. Okay. Right, part D. The energy density of a fuel is defined as the energy produced per kilogram of fuel. Calculate the energy density of dodecane, C12H26, in kilojoules per kilogram. Give your answer to two significant figures. The enthalpy change of combustion of dodecane is minus 8086 kilojoules per mole, and the molar mass of it is 170 grams per mole. Right, the first thing I would do is look at these units here. Okay, what I want to do is try and use these two numbers here to get me units that are similar to that, like kilojoules per mass. So you can see here, I've got mole and mole here. So if I take that and divide it by that, what I can do is cancel them moles out, and that leaves you with kilojoules per gram. So that's what I'm going to do. So I'm actually using the units to come up with the formula. So this is quite tricky, this actually. So we're going to start with 8086. And we're going to divide that by 170. Now I'm going to put the units on just to kind of show you what I mean. So kilojoules per mole. There we go. And then this one's going to be grams per mole. Okay. So what we're going to do is we're going to, you can see here that we can cancel that out and that out. And what we're left with is kilojoules per gram. So there's the kilojoules bit and there's the per gram bit. So what we're going to do, work that out, and you should get a number of 47.5647. And that should be kilojoules per gram. Now the problem is we don't want it per gram, we want it per kilogram. So a way in which we can convert something where it says g to the minus 1 into kg to the minus 1 is I have to multiply this number by 1,000. So 47.5647 times by 1,000. That will tell me, or that will get me into kilograms. So that's obviously, we're just going to shift the decimal point 3 places. So that's going to be 47564.7 kilojoules per kilogram. Okay. The answer wanted it in two significant figures. So this to two significant figures, we take the first two, 4 and 7. The number afterwards is a 5. It rounds the 7 up to an 8, and all the rest is converted into zeros. So that's just going to be 48000. So let's put that number in there, 48000, and that's kilojoules per kilogram. You get 3 marks for that. You get 1 mark for this answer, 1 mark for multiplying by 1,000, and you get 1 mark for your answer as well, which is must be to two significant figures. If you give your answer like that, although it's right, you lose the final mark because they did ask for two significant figures. So, yeah, so you get 13 marks in total for question 21. So, yeah, that's it. Right, let's go on to question 22. Okay, so this is question 22. 22 starts by saying Born-Haber cycles can be used to determine experimental values of lattice energies. The diagram below shows a Born-Haber cycle for the formation of strontium chloride from strontium and chlorine. Right, you can see this whole sequence of different events here with delta H's everywhere. Okay, so we're saying using the symbols from delta H1 to delta H7 as appropriate, identify the enthalpy change of atomization of strontium. Okay, so, right. Atomization of strontium. Basically, that's going strontium from a solid to strontium to a gas. That's atomization. So, here's strontium here. There's the step. So, the answer is delta H2 for that one. Okay, so let's put that on there. Delta H2. The bond enthalpy of chlorine. Right, bond enthalpy is breaking a chlorine. We're going to look for where we can, or where we have broken that. So you can see here, there's Cl2 gas, and that's gone to 2 Cl atoms. So we've clearly broken a bond there. So that's delta H5. So we're going to put that there. Okay, first electron affinity of chlorine. So this is adding an electron to a chlorine atom. So this is normally somewhere at the top here. So you can see here, there it is, 2 Cl, and we're going to form 2 Cl minus. So we've added an electron. Look, there was the 2 electrons before. They're not there now because they're attached to the chlorine. But you can see here that this delta H6 represents the electron affinity of both chlorines. We just want to look at the first electron affinity of just chlorine atom. So it's effectively delta H6 divided by 2, because we've got to take into account just one of them. So delta H6 divided by 2, or you could put half delta H6. That would still get the answer as well. Okay, enthalpy change for the formation of strontium chloride. Right, so we're looking for the, what does it say? The enthalpy change of formation of strontium chloride. Okay, you've got to be really careful with this. This is the lattice formation, this bit here. Okay, or lattice energy, or lattice enthalpy as it's also known as. So this is going from ions in the gaseous state to form a solid ionic product. This is enthalpy of formation. So this is going from elements in their standard states, look, solid and gas, to a compound in the solid phase, or a solid, or just an ionic compound, 1 mole of an ionic compound. So this one is delta H1. That is the enthalpy change of formation, delta H1. Okay, so 4 marks for that. It's not too bad. A bit of understanding of, obviously, Born-Haber cycle. Right, so the next bit is the table below shows the energy changes that are needed to determine the lattice energy of strontium chloride, SrCl2. Okay, so we've got loads of energy changes here. There's loads of numbers here. Okay, so we've got to define the term lattice energy. Okay, so lattice energy is basically, you need to remember these definitions, but it's the energy change for the formation of 1 mole of compound from its ions in the gaseous state. It's 2 marks. So let's write that down there, and I'll show you where the marks come in. So we said it was the energy change for the formation of 1 mole of compound from its ions in the gaseous state. Alright, so I suppose some really important things here is 1 mole, that's important, and gaseous state is the second mark. You've got to make sure you put them terms in there. They're really important, and they obviously help to define the lattice energy as well. So that's really important. Okay, so right, and then it asks, which is no surprise, I suppose, seeing as though they're giving us all these numbers, is to calculate the lattice energy of strontium chloride in kilojoules per mole. Okay, so the lattice energy is this last step here. This is delta H7. So this is this bit here. Now, how we work this out is dead easy. So we're starting from here, and we're going to go down to here. That's the value we want to work out. Because we can't go that way, we have to go the opposite way. See, it's like a roadblock. So if I start from here and this road's closed, because I want to work this bit out, let's imagine that's closed. What I have to do is take a diversion to get to my destination. So I go this way instead, all the way around here. But the difference is, when I go against an arrow, all I do is I just change the sign. I keep the number the same, but I change the sign when I go around. So what I'm going to do is I'm going to stick my numbers in here, and I'm going to show you kind of obviously how it works. So I've already got the obviously if we look at the table that's on there. Okay, so you can see that we've got delta H6, which is this bit. So this was minus 349, which is the electron affinity of chlorine. Remember, this is the first one. So I'm going to put, because we're going against the arrow, I'm going to put plus 349. Okay, and we're going to have 2 of them. because we're doing electron affinity of both chlorines. Remember that number that we've been showing is just for one. Okay, so we're going to do plus for that one because normally it was a negative value. If I come down here, there it is, negative. Because I'm going against the arrow, I'm going to put plus instead. Okay, the next bit, which is delta H5, this bit was the atomization, or the bond enthalpy, should I say, of Cl2 to form 2Cl. Now, because we're doing it because we're forming 2, we have to double the number that we've been given. So the number we've been given was this one, the enthalpy change of atomization of half a chlorine, but we've got a full chlorine. So we have to do 2 lots of 1, 2, 2. Now, we see that one was a plus. We're going against that, so this is going to be a minus. So it's going to be 2 lots of minus 1, 2, 2. Okay, because we're going against the arrow. So the positive one was going with the arrow, we're going against it. Next one, so this is delta H4. So delta H4 was the second ionization energy of strontium. So that's plus 1064, so we're going to do minus 1064 because we're going against the arrow. Okay, the next one was delta H3. So this one was 550, first ionization energy of strontium. So that's that one, first ionization of strontium. So that one's going to be minus 550. Because again, it was positive in the table, but we're going against the arrow. And the final one, which is delta H2, is the enthalpy change of atomization of strontium. That's plus 164. We're going against the arrow, so it's minus 164. Okay. And then we've got our last step to get to our destination, which is this one. We're going with the arrow with this one. So this one is delta H1, which is this one, the enthalpy change of formation. That's minus 829. Because we're going with the arrow, we keep that number the same. So that's going to be minus 829. Okay, so what we're going to do, basically we're going to throw all these numbers in. That's my northeast accent coming out. We've got all these numbers here, and we're going to multiply obviously this by 2. We're literally going to put these numbers in the calculator. So you do 349 times 2 plus, or plus minus 2 lots of 122 minus 1064 minus 550 minus 164 minus 829, and that should give us our answer. So I'm just going to, kind of, because there's a lot of numbers there, I'm just going to put all these numbers down here. So we've got okay, let me just double check, make sure we've got that as positive, because I think that first one was, yeah, it was positive. Okay, right, so that one's going to be positive. So we're going to have 2 times by 3, 4, 9. Okay, so that was the first step. And we're going to minus that away from 2 times by 122. Because I think that was the negative, wasn't it? Yep, minus 222. Okay, 122, sorry. And then we're going to do, obviously, minus 1064, minus 550, minus 164, and then we're going to do minus 829. Okay, and if you put all that in your calculator, you should come up with an answer of 2153 kilojoules per mole. And so that number should fit in there. Okay, that gets you 2 marks. So you're looking for all these numbers. Just make sure you're multiplying the right numbers. Read the data really carefully, and obviously make sure you get your right answer as well. So that's negative. Okay, right, on to the next bit. So this is part C. So part C is saying the lattice energies of sodium fluoride and magnesium fluoride are shown in the table below. Okay, so we've got these two here, and we've got lattice energies here. So explain in terms of the sizes and charges of the ions involved why the lattice energy of MgF2 is more negative than that in the NAF. Right, this one's basically going to release more energy when it's been formed, and obviously it needs more energy as well when you break it. So we need to basically just explain why it needs more energy to break it than NAF does. Now, the reason why is actually magnesium as an ion is smaller than sodium. It's got more protons, so it pulls them the size of the atom or the outer electrons further in towards the nucleus because it's got more protons than sodium. So therefore, it's going to have a smaller ionic radius. Now, this is quite important because magnesium's got a 2+ charge, it's in group 2. Sodium's in group 1 as a 1+ charge. So magnesium has a higher charge density than sodium, which means it's got more charge per area. So that, in terms of a bond, is pretty strong because you've got a much stronger electrostatic force of attraction between the ions in magnesium and fluorine than you do between sodium and fluorine. And that's because of this higher charge density in magnesium. So it's a 3-mark question. So we're going to structure it in terms of so you can see where you get your marks from. So Mg2+ is a smaller ion than Na+. Okay. Mg2+ has a higher charge density than Na+. Okay, and then we need to say so electrostatic forces of attraction between ions is stronger in MgF2 than in NAF. Oops. Okay, so that's the type of thing we're looking for. So you can see, 3 different things. Be methodical. Talk about, right, magnesium is a smaller ion, therefore it has a higher charge density, therefore the electrostatic forces of attraction are stronger. So it's this methodical process. You state what you've what the obvious thing is, I suppose, and then you try and go in to explain it. So it's just structuring your answers to make sure you get the best out of them as well. But there we go. You get 11 marks for question 22. Right, so we're on to question 23. Okay, so this is question 23. Okay, this question is about alkenes. Right, so 23, give the general formula of the homologous series of alkenes. Right, so this is something you just have to really remember. So this one is going to be CnH2n. Basically, you've got twice as many hydrogens as you do carbons. Okay. Part B, give the structural formula of the organic product formed when ethene, CH2 double bond CH2 reacts with hydrogen. Right. So when we react your alkene with hydrogen, what we're doing is adding hydrogen to the double bond. And so what we'll get is just an alkene. And now the key thing with this is structural formula. Look, if I circle that there, structural. Okay, so you've got to make sure that obviously we're drawing a structural formula and nothing else. So the structural formula for this is going to be CH3, CH3. So it's 2 dots of CH3. Okay, next one is chlorine. Right, very similar to hydrogen, except instead of adding H2, we're going to add Cl2. So the structure is actually remarkably similar. CH2Cl, CH2Cl. Okay, make sure it's structural. Okay, we can't draw it any other way. Right, when we add acidified aqueous potassium manganate. Now, when we add this to an alkene, what we form is a diol. And diols are basically, you've got 2 alcohols. Now, you've got to make sure you draw this really, really carefully. Okay, so we've got CH2, CH2, OH. Now, when I say carefully, what I mean is you can't put OH, CH2 like that. You can't do that. That's not allowed. because that implies that you've got a carbon bonding with a hydrogen. Obviously, hydrogen can only bond once. Can't bond to oxygen and carbon at the same time. So it must be done that way around. You've got to be really careful with that. If you do it the other way around, you won't get the mark for it. Okay, so let's delete that so it avoids any confusion. And then the last one of this part is IV, bromine water. Right, now this is weird. Bromine, we know bromine to double bond, it actually reacts in a similar way to the chlorine one that we looked at before. Because this is bromine water, we form an alcohol and a bromine. So we get alcohol on one end. Let's put that in the right colour. Okay, so you've got an alcohol there, CH2, CH2, and a Br on the end. So there you go. So you got your alcohol and your bromine and your halogen. So that's only bromine water. So again, they've emphasised that in bold. Draw it structural. Okay, can't emphasise that enough. If you draw all of them not structural, you wouldn't get a mark. So you got to make sure you do read the instructions carefully. Okay, so part C. So when propene, which is CH2, reacts with hydrogen chloride, there are two possible products: a major product and a minor product. Got to got to draw the displayed formula of these products. Can't keep your tongue in. Right, so what decides whether it's major or minor is the intermediate. In this mechanism, we go via a carbocation intermediate. If the carbocation is tertiary, that is the most stable form, and therefore you're going to get more products via a tertiary carbocation. If you can't form a tertiary and you can form a secondary, then secondary is the next stable, most stable intermediate, and you get a lot of that. And then primary is the least stable. Now in this example, we can only have secondary or primary carbocation. So we're going to get more product formed via a secondary carbocation than we are via a primary carbocation. So in that case, we're going to get more secondary haloalkanes or halogenoalkanes than we are primary. So the major product for this is going to be, remember we're drawing a displayed formula, so we have to show all the bonds. So the major product is going to be this is chlorine with hydrogen. So you're going to form your secondary halogenoalkane as your major product, and your minor product is going to be a primary halogenoalkane. Now, because this is displayed, you must show all the bonds. I know it's a bit of a pain because there's a lot to draw, but that's basically where you get your 2 marks from. So one for your major, which is your secondary haloalkane, and one for your minor. Okay. Give the mechanism for the reaction of propene with hydrogen chloride, which forms the major product. Right. This is what I was talking about before, where we have this secondary carbocation. So this is a good opportunity to kind of show you as well. So, right, what I'm going to do, I'm going to just draw it displayed because it helps to see what's going on here. So we've got obviously a double bond there, hydrogen, a carbon with a hydrogen, and another hydrogen. Okay, we're going to add HCl to this. Now HCl has a delta positive hydrogen, delta negative chlorine. Chlorine's more electronegative. Okay, we're going to basically draw our mechanism. Now mechanisms have curly arrows. Curly arrows always start from an area of high electron density. So in this case, the high electron density is in the double bond. So the arrow is going to go from the double bond and it's going to go to an area of low electron density or electron deficiency. And that's going to be the delta positive hydrogen. Now, what's effectively happening there is that bond, that will try and form a bond with the hydrogen. And so therefore you'll have to break a bond with the chlorine. So let's show you what I mean. So here's comes from your delta positive, from your alkene, from this bond here, to your delta positive hydrogen. That's effectively trying to form a bond with hydrogen, so it has to break this bond. It must go from the bond to the chlorine. Make sure you draw it that way. You've got to be really specific with where your arrows are going from and where they're going to. Okay. Now, what we're going to do is we're going to form our intermediate. Now, this is the important bit. So, obviously, the CH3 bit on the end of the molecule remains unchanged, but this bit does matter. Okay, we have a single bond now because that double bond is effectively been broken. The hydrogen is going to land itself on the end carbon there. Okay, and what that's going to leave is a carbocation, but this carbocation is in the middle. Look, secondary carbocation, much more stable than forming a positive charge on the end, which is primary. So this is going to be that one. This is going to give us the major product. And then we've got obviously our Cl minus. Lone pair. Make sure you show your lone pairs and your chlorine and your negative charge. The electrons, again, same deal. Goes from the lone pair of electrons, that's where the electrons are, to an area of electron deficiency. So this is the delta positive carbon. And let's just finish this off and show our product. So our product would be this with your chlorine attached to the bottom and your 3 hydrogens. And there we are. This is 2-chloropropane. So you get 3 marks for that. I think, yeah, you get 3 marks. You get 1 mark for basically drawing these arrows here, showing the obviously where the electrons come from the double bond and breaking this bond here. 1 mark for your intermediate, making sure you show your positive charge on there, and 1 mark for this bit here. So your curly arrow going from the lone pair on the chlorine. Don't forget the lone pair and the negative charge. So that's where you get your 3 marks from. Okay, right. The next bit. So this is part D. Okay, so part D, propene can be polymerized. Write a balanced equation for the polymerization of propene to form polypropene, drawing the displayed formula of the repeat unit of polypropene. Right, displayed formula, remember, is showing all the bonds. So this is only of the repeat unit though, so that's fine. So let's go for, right, we're going to start with our monomer. Now, our monomer is propene, sorry. So we're just going to put propene. So that's going to be C3H6. That's propene. Okay, and obviously that's going to form our polymer. Now, for polymers, you need a lot of these. So normally we represent it with an N. N means we need a number of them. So we need quite a few of them. Now, this is where you're going to get your marks from. So we need to show our displayed formula. So what happens is the double bond in the polymer, or in the monomer, sorry, opens up, and we now have what we call trailing bonds, long bonds either side of the alkene. Polymers are always shown, or repeat units are shown in square brackets. Obviously, we'll put our hydrogens on there as well. It's quite important. So it always shows in square brackets. Square brackets show us what the repeat unit is. Basically, it's this unit that repeats over and over and over again. And it's going to repeat by n number of times. Basically, the same number as what you had monomers at the start. That's all we're saying. So if we had 20 of these, you'd have 20 of these joined together. Trailing bonds, you get a mark for your trailing bonds. You get a mark for the structure here. And you get a mark for putting, obviously, the rest of it here, which is including the ends, which show basically how many of them you've got repeating. So, yeah, very important to show your trailing bonds. It must extend beyond the square bracket. Very important. Okay, next bit. State the problem associated with the disposal of waste polypropene. Right. Polymers, like addition polymers like this one here, are notorious for being non-biodegradable. So they don't degrade, and that's obviously going to cause a few problems. If I can write things properly, biodegradable. Okay, so these are non-biodegradable. Also, you might want to think about things like when you incinerate them, they produce bad toxic fumes. They take a while to break down, like thousands of years. They can harm wildlife as well. So these plastics, you'd see some river birds getting stuck on these plastic can holders that people throw away, and they don't degrade, and they get some wrapped around the neck. So these things are pretty bad in that form, and I suppose chemists are out there trying to find alternatives which are perhaps that biodegrade, and there are biodegradable plastics out there, to be fair, or we recycle them, and that's why it's important to recycle, chop them up and reuse them, so they're not going to be lying around in landfill. Okay, so that's that one. And then part E. So part E is looking at your, obviously, standard enthalpy changes here. So standard enthalpy changes of combustion can be used to calculate the standard enthalpy change of formation of propene. So you've got carbon, hydrogen, and propene there at the end. Values for some standard enthalpy changes of combustion are shown in the table below. Okay, so we've got all them values there. Complete the Hesse cycle below to enable you to calculate the enthalpy of formation from combustion data. Right. Here we go. Elements, and we've got our alkene there. There's our enthalpy of formation. The data they've given us is combustion data. So when we draw a cycle, we always draw arrows pointing downwards, and they point down to combustion products. Now, combustion products, we assume that they burn completely. Okay, that's one of the assumptions we make. So combustion products, we produce carbon dioxide and water. So in this example, let's put our arrows pointing down, because these are always the case with all combustions. If it was formation data they've given you, so this data here, if it was formation, the arrows would point up from elements in their standard states. Okay, so that's pretty important. So anyway, this is combustion now, so the products are going to be carbon dioxide, which is obviously gas, and water, which is obviously a liquid. Now we need to make sure these balance. So you can see we've got 3 carbons here, so we need to have 3 there. And you can see we've got, look at the number of hydrogens, we've got 6 hydrogens there, so we need 6 here, so we need a 3, because that's 3 lots of H2. We do have oxygens as well. We do burn these in oxygen, but the number of oxygens on the left and the right, they balance out. So that's where the oxygens come from on here. So you can put them in if you want, but we normally omit them because they do cancel out either way as well. So we don't normally include them. But yeah, there you go. There's your Hesse cycle. Carbon dioxide, water. Make sure they're balanced. Make sure you've got state symbols and everything like that. Okay. Right. And this is, the last bit. Calculate the enthalpy of formation in kilojoules per mole. Right, so this is relatively straightforward. I'm going to use a different coloured pen. Okay, let's use green. So you can see here that we've got 3 lots of carbon burning to form 3 lots of CO2. So we're combusting 3 carbon. Minus 394. So what we've got is 3 times by minus 394. Because we've got obviously 3 lots of that. And that's going to produce minus 1182. Okay, we've also got 3 lots of hydrogen as well. So 3 times by minus 286. Okay, and that's going to give us minus 855. Add all that up, we should get minus 2040 kilojoules per mole. Okay, look on the other side. Combustion of ethene is very straightforward. We've only got 1 molecule of that anyway. Is 2058. Okay. Okay, so all we have to do is we use the cycle to calculate the enthalpy of formation. So if we start from, obviously we want to work out going from here to here. Imagine a bit like a roadblock, so we can't go that way, so we need to go down here and up here to get to this product here. So when we go with the arrow, we keep the sign the same. So that's just going to be minus 2040. We go against the arrow, we change the sign, flip that sign to a positive. So we're going against the arrow to get back up here. Plus 2058. Okay, so add all that up and we should get plus 18. So that's your answer. So you get 2 marks, 1 mark for working out this bit and 1 mark for obviously getting your answer right. So that's the end of question 23. So we've just got one more question, which is question 24. Okay, so this is the final question, 24. It says the diagram below shows the pattern in the first ionization energies of the first 18 elements. You can see they've given us obviously all the data there. Okay, and the atomic number, etc. So give the equation, including state symbols, for the first ionization energy of fluorine. Right, okay. So really important, 2 marks. You've got to include state symbols. So this is obviously going to be fluorine. It's all in the gaseous state, which makes it a little bit easier. We're going to remove an electron. Now, when we remove an electron, we obviously form a positive ion. And obviously, we're going to form an electron as well. So you get 2 marks for this. 1 mark for the state symbols and 1 for the actual full equation. Okay. And part B. Explain why there is a general increase in the first ionization energies from sodium to argon. So why is that general increase? Well, we've got to say, as we go across the period, we have more protons as we go across. But the shielding, which is basically the number of electron shells between the nucleus and the outer electron, is the same. Okay, so that's really important. Shielding is so important here. And basically, because the shielding is the same, it's going to have no impact. but we have a greater attraction between the nucleus and the outer electrons because of that increased positive charge or nuclear charge, because we've got more protons. So there's your marks there. So we're going to write them down on here. So the number of protons in nucleus increases. Okay, so this shielding business is really important. Okay, so same shielding. We can say we've got the same number of electron shells. Okay, and then what that means is we have greater attraction between the nucleus and electrons. Okay, really important. Shielding, even though shielding has no effect on these molecules here, we've still got to include them in our answer because we've got to comment on them, even though it has no impact, because it is important. It basically explains, well, obviously why we have an increase in first ionization across the period. So, right, on to the next question. So this is part C part 1. So it says, explain why the first ionization energy of aluminium with Z13 is less than that of magnesium with Z12. Right, so let's have a look. So aluminium is Z13. There it is. And we've got magnesium Z12. So we need to know, why has this got a lower ionization, first ionization, compared to this one at the top? Right. The first thing we're going to look at is the subshells. So these two electrons here are in the S subshell. The other ones, all these ones, are in the P subshell. Now the P subshell is a little bit further away from the nucleus than the S subshell. And the P subshell is actually shielded from the S as well. So if we're trying to remove an electron from something that's slightly shielded from the positive charge of the nucleus, it's going to be a little bit easier to remove that electron. And that's exactly why we have a lower ionization here than we do here. So let's get that into words. Okay, so the electron is lost from a 3p subshell. Okay, so this is further. Supposed to be a H. There you go. This is further from the. This is further from the nucleus, and is shielded by the 3s orbital. Okay, so this is 2 marks. So we need to say that the electron is lost from a 3p subshell. So that's the first mark. And this is further from the nucleus, gets the second mark, or you can say shielded by the 3s orbital. So that's where you would get your 2 marks from. Okay. Then it goes on to say, explain why the first ionization energy of sulfur, Z16, is less than that of phosphorus, Z15. Right. So let's have a look. So it's Z16 and 15. Okay, so there it is there. 16 is there and 15 is there. Now we need to say, why is this lower than that one? Basically, what we've got, they're both in the p orbital, but as you may know, with the p orbital, you've got, or with the p orbitals, you've got basically a system where we fill singly first, because you've got 3 of these. And they fill up singly first, and then the 4th electron has to go into an orbital with an electron already in there. And obviously these electrons repel each other because they're both negatively charged. So it's actually easier to remove an electron from a a paired orbital than it is from a non-paired orbital because of the repulsion that's happening there. So that's why it drops a little bit here, because we do have an electron in one of them paired orbitals. So let's get that into words. Okay, so electron lost in an orbital with electrons paired. So there is electron repulsion, and the electron is lost more easily. Right, really important. 2 marks there. So we're saying electron is lost in an orbital with electrons paired, 1 mark. And then the electron repulsion, that's really important. An electron is lost more easily. So that's why we have 2 marks there. Okay, right, on to part D. The table below, which is incomplete, refers to the elements sodium to sulfur. Okay, so obviously we've got all these elements here. We've got sodium, magnesium, aluminium, silicon, phosphorus, and sulfur. So what we need to do is we need to, as you see here, the first bit, complete the melting temperature row by using only the words high or low. Right, we've got sodium, magnesium. Sodium is quite soft as a metal, so it has a low melting temperature. Magnesium is high. Aluminium is a metal as well. Obviously, we know what aluminium looks like. It also has a high melting temperature as well. Silicon is a giant covalent structure. It's huge. Really, really high melting temperature. Lots of energy required to break the many strong covalent bonds. Phosphorus is just very small, simple molecular, so that one is going to be low. Sulfur is the same. Low melting temperature. Okay, part 2. Complete the structure row by using only the words giant and molecular. Right, sodium is a giant metallic structure, so that is giant. Magnesium is giant metallic. Aluminium is giant metallic as well. Silicon is giant covalent, so that is giant as well. Phosphorus is molecular. Okay, it's a very simple, small little molecule. Okay, sulfur is the same. Okay, so that's that one. And then part 3, complete the electrical conductivity row by using only the words high and low. Okay, right, so sodium, electrical conductivity, it's a metal, so it would have a high electrical conductivity. Aluminium is a metal, that would be high as well. It's got free electrons, delocalized electrons, that's what allows them to conduct electricity. Phosphorus and sulfur don't. They don't have free electrons or free moving ions, so they have low electrical conductivity. That's for both of them. Okay, so you get 5 marks for that, just for obviously knowing your properties, etc. So you really do need to make sure you know about the properties, physical properties of these things. Okay, and then part E. So part E is obviously looking at mole calculations. So it says in an experiment, 2.76 grams of sodium completely reacted with water to form 500 centimeters cubed of aqueous sodium hydroxide. So we've got all the reaction there. And then part 1, it says calculate the number of moles of sodium that reacted. Okay, so really, it's not too bad, this question. So we're looking at moles is mass divided by the relative atomic mass, or AR. So the mass in this case is 2.76. Divide that by the AR, which is 23. That's the AR of sodium, so find that in the periodic table. And if you put that in your calculator, you should get 0.12 moles. Okay, so that's the moles of sodium. Part 2. Calculate the maximum volume in decimeters cubed of hydrogen that can be formed at room temperature and pressure. So we're going to use 1 mole of any gas occupies 24 decimeters cubed at room temperature and pressure. Right. Now, what we can do is we need to work out the number of moles first of this gas which is hydrogen. So we know the number of moles of sodium, but we know that's a 2-to-1 ratio. Look, 2 moles of sodium, 1 mole of hydrogen. So the number of moles of sodium, the number of moles of hydrogen is going to be half that of sodium. So let's put that on there. Moles of hydrogen equals 0.12. Divide that by 2, and we should get 0.06 moles. Okay. And then once we've done that, to work out the volume, because the volume of any gas occupies 24 decimeters cubed, 1 mole of any gas, at room temperature and pressure, then the volume is literally just 24 times by 0.06 moles, and that's going to get us 1.44 decimeters cubed. So you get 1 mark for obviously working out your moles of H2, and then 1 mark for your final volume. Okay, and the last question. Part 3. Calculate the concentration in moles per dm cubed of the sodium hydroxide solution NaOH formed in the experiment. Okay, right. So again, we need to work out the number of moles of sodium hydroxide. You can see a pattern here. Working out the moles. Once we know the moles, we can work out loads of things from the moles. So number of moles. So let's put that on there. Moles of sodium hydroxide. Right, let's have a look at the equation. There it is. Look, sodium hydroxide 2. Sodium's 2 as well. So basically the number of moles of sodium is going to be the same as the number of moles of sodium hydroxide because it's a 2-to-2 ratio. So that's going to be 0.12 moles. Okay. And then the concentration is, remember, is the number of moles divided by the volume. So the number of moles is 0.12 divided by the volume. Now the volume I think was 500. Yeah, look there, 500 centimeters cubed. So that's what we're going to do. That's what we're going to use. So it's going to be 500 times by 10 to the minus 3. That means the same as dividing by 1,000 because we need to convert this into decimeters cubed. So that's why I've put times by 10 to the minus 3. So we'll put that on there, and then we should get a number of 0.24 times, nope, that's it, 0.24, and that's moles per dm cubed. So that's your concentration there. And so, yeah, that's the end of that paper. So, I suppose in summary, things like you've got to watch out for are things like obviously units, significant figures, obviously important. Make sure you give it to the appropriate number of significant figures. Make sure you read the question really carefully. You only give the answers what they're after. Don't write everything that you know. Especially with things like periodicity, keywords like shielding come up, even though you might think, well, shielding has no effect. Mention it, write it down, talk about shielding, look at the keywords we're putting in here. That's all examiners are looking for. Obviously put them in the right context. That's obviously very important. And your multi-choice, just look at the multi-choice and try and read it really, really carefully. Make sure you are not missing any little bits of information that could scup you, because they will put in questions that you will calculate and you might get it right, but it might not be exactly what they're after. So just make sure you're reading it really carefully and you're not thrown off by them kind of, I suppose, answers that are very similar. But that's it. Bye bye.